Hi everyone, welcome back. In this video, we're going to continue exploring propositional logic, specifically the branch of propositional logic that deals with truth tables. So we're going to do a little bit of review just to sort of jog our memory regarding the basics of the truth functions for each of the logical operators that propositional logic covers. And then we'll move a little bit forward and see if we can't get a little bit more of an understanding of the main operator as the key driver, the key operator of a complex sentence. All right, so just to review, first, propositional logic translates statements into symbolic form, right? That's really what we're up to. We're taking parts of the language and sort of formalizing them into variables that are connected under the aspect of logical operators, right? The logical operators help us in bringing together parts of a complex sentence. Logical operators are used to represent connectives between statements, so we can build up from simple statements to complex statements with logical operators. And we learned that there are these different operators that we translate with various symbols. The main operator is sort of the most important single operator in a complex sentence. The main operator governs the meaning of a compound sentence, right? And the the grammar of propositional logic suggests a number of rules that we need to follow in order to have what's known as a well-formed formula. In other words, we can't just be using our operators in any old place. We need our operators to be positioned in such a way that we understand the meaning of the proposition. So well-formed formulas specify rules for our operators, and we sort of went through some of those rules. Some of those rules include the idea that we need to have negations, the tilde, situated to the left of the statement that it is negating. For symbols like conjunction, conditional, and disjunction, we need those to be in between two variables, right? So we need the usage of proper placement for our operators. And 5, truth function tables assign a truth value to compound propositions. So what this means is that for all of our 5 operators, we have a kind of truth function such that we can come to an understanding of when a particular operator is either true or false. And we're going to be exploring a little bit more in this video what we can do with that. We can apply the truth value functions to more complex statements. And ultimately, we're going to be able to pick up what complex arguments are valid or not on the basis of their truth value. Okay, so just to sort of rehash the truth functions for our operators, if we have a look at the negation is represented with just our tilde, our red tilde here. On the left, we have the reference column, and for any single variable p, remember p is an arbitrary letter we're using just to indicate one single variable. P can either be true or it can be false, right? And so always remember on our reference tables, when we're building them out, we need to begin with a true value. And I'll talk a little bit further about figuring out just how long our reference tables have to be to build a proper truth table. But for a single variable, we only have 2 options. The variable can either be true or false. And then the negation of p is simply the opposite of that value, right? To have a true variable p negated means that that true p becomes a false p. The negation of a false p becomes a true p. So negation is actually pretty straightforward. It just takes the opposite value, right? Negation is the inversion of our given truth function. Okay, so those are the truth table functions for negation. If we have a look at conjunction, it gets a little bit more complex, although not terribly complex. Conjunction is bringing together 2 variables at the very least, right? Because it's a connective that is meant to be integrating 2 simple statements through a conjunction as an and or but, right? So we need our symbol dot to symbolize the bringing together of P and Q. So a conjunction is always going to have at least two variables, right? So we need two in our reference tables, P and Q, right, over here. So I'm just writing in red here the break so that you understand that on this portion of the table, we have our reference tables. Apologize, that did not come out so well. This is the reference table. And for two variables, we have to split the truth values in half. We begin with P with 2 rows for true, and then 2 rows for false. And then I like to think of it this way. For the next variable, we are sort of cutting in half the first values such that we get 1 row true, 1 row false. And then we're cutting in half the false values such that we have true and false alternating. So for any truth tables that use two variables, they will always look like this. They will always take this form. 2 values true, 2 values are false, and then for the second variable, we alternate single values, true, false, true, false. Always beginning with a true value, by the way, on the top of our reference table. So this is just basically laying out every possible combination for the truth values of two variables, P and Q. Now, when we bring together P and Q with a dot, we have to think about what the value of dot is. And we came to an understanding of the truth functionality of dot, of conjunction last time, when it was discovered that dot is only true when both of the conjuncts themselves are true. When both of the things that are being connected have true values, dot is true. So in order to flesh out the details of the values for dot, we have to compare the values of P and Q for each row. So I really urge you to not skip any steps as you're building the truth tables, because it can be very easy to make a mistake if you gloss over one of the values. So let's have a look at our first row. I have a true P and a true Q. So because the values of both of the conjuncts are true, the dot on the first row is true itself. So that is a true conjunct, right? That is the only time that dot can be true. Both of the conjuncts are true. If I go down to the second row, I see that P is true and Q is false. So because I have one false conjunct, I know that the value for dot has to be false, right? It's a very high threshold for the conjunction to be true. We need 2 true conjuncts for dot to be true. And because Q is false, dot is false. Now, if I move down to the third row, I see that under P, the value is F, so it's false, and the value for Q is true. So the value of dot as a whole on the third row is also false because that first conjunct is false. Okay, and finally, on the fourth row, I have a false value for P and a false value for Q. So I know that dot on the fourth row is false because both of the conjuncts are false. So the only row in which dot is true is that first row where I have 2 true conjuncts. All right, so that's the truth table for dot. If we move forward with disjunction, right, disjunction kind of means either or, and we use the wedge, the V symbol, to symbolize disjunction. We build our reference tables for 2 variables, PQ, to the left. Again, these are going to be exactly the same over here. These are our reference table, and they just lay out every possible truth value for 2 variables. Reference, if I can write it. So you'll notice these are exactly the same values for the previous slide, right? Because we just have 2 variables, P and Q. The first 2 rows are going to be true, and then the third and fourth rows are going to be false. And to build out the values for Q, just like we did before, we're going to split those values in half such that we get a true value in the first row, a false value on the second, a true value on the third row, and a false value on the fourth, splitting that value in half. So the reference tables are always the same for two variables, right? 2 rows of true, 2 rows of false, and then for the second variable, alternating values, true, false, true, false. I want you to get in the habit of writing these down because it'll be all the more easy to build truth tables for more complex statements if you really have the process of writing the truth table reference tables down. So now if we're thinking about what the truth functions for wedge are going to be, we have to think about our rule for wedge. And if you recall that wedge has a much lower, the disjunction has a much lower standard for counting as a true disjunction. All we need is one of the two disjuncts to be true for wedge as a whole to be true. If, however, the two disjuncts are false, then wedge as a whole is false. So in order to determine the values of wedge, we just do our comparison of all of the values on the reference table. So on the first row, we have one disjunct is true, P is true, and then our second disjunct is true, Q. So wedge on the first row is true. Both of the disjuncts are true. On the second row, we see that the first disjunct, P, is true, and the second disjunct, Q, is false. Because just one, we only need one disjunct to be true, wedge on the second row is itself true. So that's the key difference between disjunction and conjunction. We only need that one disjunct to be true, and that first variable P is true. So wedge as a whole is true. On the third row, we see that the value for P is false, and the value for the second disjunct Q is true. So because we have that one true disjunct, we know that the value for wedge as a whole, again, is true, only needing that one disjunct to be true. On the final row, we have a false value for the first disjunct P and a false value for the second disjunct Q. So finally, we have an instance where both of the disjuncts themselves are false. So wedge on the fourth row is false. So for any disjunction of two variables, the truth values look like this. They are all true except for that final row where we have a possibility of two false disjunctions creating a false wedge. All right, so take a look back and spend a little time comparing and contrasting conjunction, the values for conjunction, and the values for disjunction. They're a little bit easy to confuse and get them twisted, as it were. Just remember that conjunction needs two true conjuncts for a dot to be true, whereas disjunction only needs one true disjunct for wedge to be true. Okay, moving along here, let's have a look at the conditional. The conditionals are horseshoe. It's an if-then kind of sentence. Again, our reference tables are set off on the left for two variables, P and Q, and they are exactly the same again. We have two true values under P and two false values under the true ones, and then we split those in half such that we're now alternating values under Q, true, false, true, false. Always, our reference tables will always begin with true values. You should never be writing false values to kick off the top row of a variable. Okay, so the reference tables are always identical regardless of the operator you're exploring. For two variables, those reference tables are just referring to the possibility, the possible combinations of truth values for any two variables, regardless of the operator. Now when we consider the operator, we have to think about what is specific about that operator, right? So this is the conditional. It's an if-then kind of statement, conditional. Um, and you have to think back now on our rule. When is horseshoe true and when is horseshoe false? Horseshoe is only false if we have a true antecedent and a false consequent. In other words, horseshoe is only false when the part to the left of the horseshoe is true and the variable to the right of the horseshoe is false, because that is our classic definition for the violation of validity. That would count as a true premise generating a false conclusion. And already in our first chapter, we know that that is an invalid argument. So to run the truth functions for horseshoe, we just do our comparison on our reference table. For the first row, we have a true value for our antecedent p. So p is true. And then we have a true consequent under q. So we know that horseshoe as a whole on the first row is true. There is no violation of validity when we have a true antecedent and a true consequent. If we move down to the second row, I have a true antecedent under the value for p and a false consequent for q. So we know that this is a classic case of violating our law of validity. We have a false horseshoe on row 2. You cannot have a true antecedent and a false consequent. So this row is false. Every other row you may be noticing is true. Every other instance of horseshoe is true. If we have a false antecedent and a true consequent, the horseshoe as a whole is true. That might be a little counterintuitive. It might sound strange to you to have a false antecedent and a true consequent and a true value under horseshoe. But there is no violation of validity if we have a false premise and a true conclusion, not necessarily. And likewise for the fourth row, if we have a false antecedent and a false consequent, horseshoe is still true. This one really trips up students because we tend to think, well, if both parts of the conditional are false, wouldn't the horseshoe itself, wouldn't the conditional as a whole be false? But that's not necessarily the case. The only necessarily false horseshoe is this instance of a true antecedent and a false consequent. All right, so that's the truth value, the truth function table for the conditional. Now if we look at our last one, the biconditional, we use that triple bar to indicate the biconditional if and only if, which is really the conjunction of two conditionals. Again, this one's a little bit less common than the other operators, but you still have to know it. So we have the same deal here. To the left, we have our reference tables for two variables, p and q. We have the same variables again, the same values. 2 rows are true, 2 are false, and then we alternate true, false under q. Now we have to think back on our rule regarding the triple bar, regarding the biconditional, and think about when the triple bar is true and when is it false. And what our rule suggests is that when you have the same values, the triple bar is true. That goes for if the values are both true, and it goes for when both of the values are false. So equivalent values generates a true biconditional. So in order to determine the rows, we look at our reference table, and we see that under P, we have a true value, and under Q, we have a true value. So because those values are the same, we know that triple bar on the first row is true. This one checks out. On the second row, I see a true value under P and a false value under Q. So because those are different values, triple bar on the second row is false. This one does not work because these are different values. Okay. On the third row, I have a false value under P and a true value under Q. So again, we have a false value under triple bar. These are different values, so it can't be true. Finally, on the fourth row, I have a false value under P and a false value under Q. And so therefore, the biconditional is actually true. These are identical values, even though they're false. So be careful with that. That's an easy thing to forget. You don't need two true values. You just need two identical values for triple bar to be true. So we have two instances where the biconditional is true and two possibilities where the triple bar biconditional is false. Okay, these are the functions for our operators. Try as best you can to memorize them before the end of next week. It's very important for you to be able to use these with a certain amount of ease and a certain amount of facility as we move along with more complex arguments. So how do we use these? The main operator is the goal for complex sentences. In other words, what we're really after is the truth values for the main operator on any complex sentence. That is sort of the governing principle, the governing feature of the entire complex sentence. But there's some trickiness that we have to account for when it comes to determining the values for a main operator. The reason we care most about the truth values under the main operator is that those are the truth values that essentially determine the whole statement. So the idea is like that the truth values of the main operator are kind of the ultimate kind of subject of the statement. In other words, they are the truth values of the statement as a whole. So unlocking the secret of the truth values on our tables of the main operator sort of unlocks the meaning of the whole sentence at the level of truth functionality. So now we're going to apply the definitions of the operators so that we can determine the truth values of more complex compound statements. In other words, we're building up from the truth functions of just the operators and plugging them into more complex statements to see if we can discern the truth functions of them in their entirety. Now, in order to do this, we have to follow a rather strict order of operations. In other words, we can't just pick out whatever operator or variable we like and discover the truth values of them without following the procedure, because the way in which propositional logic is working, as you can kind of pick up on now, is that each part of the complex statement is determined by every other part. And so we have to kind of account for the ways in which certain operators are modifying less important modifiers, right? So the order of operations, according to our textbook, is a step-by-step method for generating a complete truth table. It's the kind of way in which we have to go about moving from the simple to the more complex. So the truth values of simpler statements determine the truth value of the entire compound statement. So you should think about working from the most simple to the most complex, with the main operator being the last thing, ultimately, that we build a truth table for, because that is sort of the most complex component part of the compound statement. All right, this is all sort of abstract. I think it makes more sense when you just see how it works, but we're going to work our way from the truth values of simpler statements to the truth values of an entire compound statement. And we have to do that by following a couple of rules. Okay, so how do we arrange the truth table? When we are building our reference tables, we have to follow a formula in order to determine how many rows we need on that reference table. So the formula for any proposition is going to look like this. The number of lines we need on the truth table equals 2 raised to the number of variables we have in the sentence. And we're going to use n to stand in for the number of variables. So L equals the number of lines in the truth table, and n equals the number of different simple propositions in the statement. So our formula is L equals 2 raised to the power of n. This will become a little bit easier to see how this works when we apply it. But just to give you an example, if we have 2 variables like p and q, L equals 2 raised to 2, right? And we already saw that the number of lines on those truth tables was 4, right? Because 2 raised to 2 is 4. So if we have a sentence like this, which reads, either it is not the case that both p and q, or q. All right, so we have to think about a couple of things before building out a complete truth table. We go back to our formula, and L equals 2 raised to n. Well, if we think about what n is in this context, n has to be 2, because we only have two different variables. Even though we have p, q, and another instance of q, because q is identical, it's only two total variables, p and q, right? Not 3, just p and q. All right, so in this case, we're going to have a truth table with 4 lines, right? 2 raised to 2 equals 4. So that's the total kind of number of rows we're going to need. 2 times 2 equals 4. So it's going to be 4 lines in our truth table. So you can kind of see that truth tables can get incredibly long depending on the number of variables you have. The length of the truth table is just a function of the number of variables you have. So if we look at a statement like this, we have a complex statement that's pretty similar with a negation, parenthesis, conjunction, disjunction. If I ask you what the main operator is, you should be able to pick up on the wedge being the main operator because it's outside of parentheses, right? So this kind of statement reads either it's not the case that both P and Q or R. So if we think about how many lines we need on this kind of a statement, we have to consider that there are 3 variables here, P, Q, and R. So L equals 2 raised to 3. So L is going to equal 2 times 2 times 2, or 8. So we would need 8 lines for a complete truth table for this statement. So these can get quite long quite quick, right? So most of the time we're either going to be working with truth tables of 4 lines or 8 lines moving forward. But for any complex statement of 2 variables, we will always need 4 lines in the truth table. And for any complex statement of 3 variables, we will need 8 lines. So that's always the formula, and there's nothing that changes about it, depending on circumstance. So it's just a very good way of sort of making sure that when you're building your reference tables, you're doing so with the right amount of lines and therefore the right amount of possible truth combinations. Okay, so how do we arrange the truth values? If we take this statement, either it is not the case that both P and Q or Q, we have to set up our truth table first. So again, we are going to sort of set off our reference tables here to the left. Remember, the reference table over here is just going to give us an arrangement of the possible truth values for the 2 variables P and Q. And again, because we have only 2 variables here, we only need 4 lines. 2 raised to the power of 2 equals 4. And remember how we break down the possible truth values for those variables. We have 2 rows that are true and 2 that are false. And then under Q, we are going to split in half those 2 values such that we have alternating true, false, true, false. And we split in half the false one, true, false. Okay? So again, these are our reference tables. And what that means is they are just laying out every possible truth value combination for 2 variables, P, Q. And you should think of them as sort of your compass that you will be checking back on as we plug in the values for this sentence. So this will always be the same truth value no matter what the variables are for any statement that has 2 variables, PQ, RS, XY. It doesn't matter what the variables are, it just only matters that there are 2. All right, so once we've done that, we can kind of consider our next step. We have our reference columns, and we have to think about the main operator, right? The main operator is wedge, and as you recall, the main operator is the goal of our truth table. We are really looking for the values of wedge. We know that wedge has to be the main operator because it is outside of parenthesis. This negation is really a negation of the truth value of dot. Okay, so we'll consider how that is functioning. But wedge is really what we're after. So wedge is our goal. Just going to write goal. And so because wedge is goal, it really has to be the last thing that we discover. It's the last thing in terms of its truth values that we're able to plug in, because it itself is a function of the truth values of the other statements. It itself is a function of the truth values of dot and the truth value of q. So we have to sort of, hold on in the back of our mind to wedge as being the goal, but sort of be patient with it and just set it aside for a moment. So the value for disjunction will be last. We have to find the value of dot first. Dot is the thing that is really determining the truth value of this entire statement. We are looking for, of course, just to rewrite this, wedge. This is our goal. Sorry for the repetition here, but I do believe it is helpful to kind of repeat these steps. So we have to find the value of dot, and then once we find dot, we're going to negate it, right? This negation is a negation of dot. This statement, again, reads, either it is not the case that both P and Q, or Q. So we have to be clear when we're working with parentheses what negation is a negation of and what conjunction is a conjunction of, because without that proper sense of scope, it will totally set off the meaning of wedge, right? What is the disjunction here? The value itself of the negated dot is the first disjunct, and then Q is our second disjunct. Okay, so how do we move along here? We have to find the value of conjunction before the negation because it is in parentheses. So that which comes in parentheses is simpler than that which is outside of parentheses. That which is outside parentheses is determining the truth value of what is inside the parentheses. So here's the correct order of operations. First, we find the value of dot because it's in parentheses. Then we find the values for tilde because it is a negation of dot. Then we can find the values for wedge. All right. So that is the correct order of operations. And once we have the values of wedge, we have discovered sort of the truth value of the sentence as a whole. All right. So I will show you in a moment how to do this. I kind of encourage you before moving on that you've at least written down this statement laid out as it appears here with the reference tables built to the left. The more often you can write these statements on your own with the truth table arranged properly, the easier this will all be. Okay. So let's recall our rule. If I can get out of the way here. We know from the truth functional rules of conjunction that the conjunction is only true when both of the conjuncts are true, right? So the way to discover the values that have been laid out here under dot is to do this. We plug in our reference tables the values for P and Q in order to discover the value of dot, the conjunction. So if I do a cross analysis here with the reference table, I see on the first row that P is true. So I'm going to write under P that it's true just so I can see it. And I really recommend that for every variable, you just go back into the reference table and carry over the value on each row so that you don't necessarily make the mistake of skipping over a value. I think it's very easy to write a wrong value if you don't write in what appears on the reference table. And then I see on the second variable, Q, that the value is also true. So this is right? The value for dot on the first row has to be true because both of the conjuncts are true. That's our rule. If we go down to the second row, I plug in the value for P on the second row, which is true. And then I have a comparison with the second conjunct on the second row, Q, which is false. So I'm going to write in false. So we know that the value of dot as a whole is false, right? Because we have one false conjunct when we need two true conjuncts. And then I go down to row 3, and I'm going to write in false under P because the option given on row 3 is false. And then I look under Q, and the value is true. So I'm going to write under Q true. And I know that the value for dot on the third row has to be false because this first conjunct under P is false. So this one is false. And then for the fourth row, I see two false conjuncts. And I'm just going to write them in just to be extra diligent. And this generates a false value under dot on the fourth row. Okay? So the sort of the most important value within parentheses is dot, true, false, false, false. These values were discovered by comparing the two variables P and Q on the reference table with consideration of our rule requiring two true conjuncts for dot to be true. Okay, so now we have the values for dot in place. Now we have to consider the values for tilde. And remember, tilde is a negation of dot. You have to be careful about this. Tilde is not a negation of P, and tilde is not a negation of Q. It is a negation of all of these values. So in order to discover the values for tilde, we are just simply going to negate the values of dot on each row. So what is the first value for dot? It's true. The negation of true is false. So the first value for tilde is false. If we go down to the second row, I see that the value for dot is false. So the negation of a false dot is true. The second row of tilde is true. Remember, with negation, it's always just the opposite of whatever value is given. On the third row, I see that dot is false. So again, tilde is true. It is the opposite. And finally, the last value for dot is false. So tilde is true. So these are the values for tilde. False, true, true, true. Okay? We're getting closer to discovering what the values are for wedge. So let's consider wedge in relationship to Q, which is our second disjunct. Remember, this is our main operator, or our goal, and Q is our second disjunct. Second disjunct. And really, our first disjunct is tilde. Tilde is kind of the governing set of values of this statement. So really, we're going to consider this the first disjunct. So when we consider the values of wedge, we're going to be comparing not the values of P, not the values of dot, not the values of Q, but tilde. So in other words, all of this has been building up to these values, and then we're going to compare these values with Q. So in order to find the values for our main operator, we still have to consider the values of Q as the second disjunct. So to do that, this part's pretty easy. We just plug in the values for Q from our reference table. Some people like to skip this part because you can just kind of eyeball it, but I really recommend rewriting the values for Q as they appear here in order to avoid any easy mistakes. So on the first row for Q, we see that on the reference table, Q is true. On the second row, Q is false. On the third row, Q is true. And on the fourth row, Q is false. Okay? So now we are comparing under the disjunction, under the idea of either or, the values for tilde and the values for q. So we have to remember what our rule is for disjunction. Disjunction is only false when both of the disjuncts are themselves false. As soon as there is one true disjunct, the disjunction, the wedge as a whole, is true. So let's do our comparison to see what the values for wedge are. On the first row, I see a false tilde, so our first disjunct is false, but our second disjunct q is true. So the first value for wedge is true because we have that second disjunct with a true value. On the second row, I see a true tilde. First disjunct is true. And under q, I see false. So again, we have one true disjunct and one false one. So the value of wedge as a whole is true because all you need is that one true disjunct. Now we have on the third row a true disjunct under tilde and a true value under q. So wedge as a whole is true. All right, both of the disjuncts are true, so therefore wedge is true. And finally on the fourth row, I see a true tilde and a false q. We have a true disjunct and a false disjunct, so the value of wedge as a whole is true. So this is true on every row. Now it's important to differentiate the values here by boxing the values of your main operator. This will help sort of organize the truth table in a way that's a little less chaotic. Put a box around or a circle around the values for the main operator. So this is really the key to the whole sentence. Wedge is true on every row, on every row of this sentence. So this is a complete truth table for this sentence. Either it is not the case that both P and Q or Q. Okay? So let's have a look again. This is just sort of a recounting of what we've done. Because the wedge is our main operator, we have to think about which operator is determining the value. Define the value of the main operator in wedge. We have to compare values of Q with negation. Right? So I think the tricky thing about this sentence was coming to see that really the things to be compared were the values of tilde with the values of Q, where Q we plug in from the reference tables true, false, true, false. If we were to compare the values of dot and Q, we would get a different story, right? Wedge would be true, false, true, and false. That is a very different set of values than what we just discovered. So that would be a completely incorrect truth table for this sentence. It does not have that meaning. It has the meaning of bringing into a disjunction the negated values of dot, not the values of dot, right? They're the opposite values, all right? So to find the value of the main operator, the wedge, we have to compare values of Q with negation, okay? So this is the complete set. I won't rewrite the values for Q here, but as you can see, they're just plugged in from the reference table with the result that the values for the main operator are true in every instance. Now, the technical term for a complex sentence that is true in every row is a tautology. A tautology is true by logical definition. So this is kind of an instance where a bit of circular reasoning has taken place, and in a sense, the sentence isn't really giving us any new information, whatever its content is, because there's no instance in which the value of the main operator is false. And when it's only true, it's kind of not saying anything. It's sort of just spinning its wheels. So this is a tautology or a logical fallacy. Okay? Because the disjunction is only false when both of the disjuncts is false, all possibilities of the main operator are by definition true. And thus, it's a tautology. We'll talk a little bit more about some other ways in which a complex sentence like this can be a fallacy. there will be an example of self-contradiction where we have only false values, right? You don't have to worry about that quite so much at the moment. I just want you to see that when you do have all true values, you're working with a tautology. All right. So let's just have a look at one more example, and I encourage you to sort of write this out with me as we're working so that you can see how this works, because I believe this is really a skill set. It's really a practice. It's not really just a collection of ideas. There's really only one way to learn and understand the truth table, and that's from writing them yourself. Okay, so if we have a sentence like this, either P or if Q then not P, we build out the truth table by writing the full sentence out to the right. And then we refer back to our formula to determine the number of rows we need. L equals 2 raised to n. And in this case, the number of variables is 2. So L equals 2 raised to 2. So L equals 4. We're used to the 4-row truth table now. So again, we have the reference tables here for P and Q. Just so you're clear, these are the reference tables. And again, we're going to build out our reference tables in exactly the same way, with 2 true values at the top in the first 2 rows, and then 2 false values for rows 3 and 4. And then we split these rows in half under the second variable Q such that we have alternating values, true, false, true, false. These are exactly identical as the last set of truth tables for the reference columns, because it's the same number of variables too. Okay, so once you have written out those reference tables, now we consider what our order of operations is going to be for this sentence, either P or if Q, then not P. So remember, what's our first question? Our first question is, what is the main operator? What is the most important operator in this sentence? You should be able to identify that it's wedge again. We're going to be working with disjunction again, because this is outside of parenthesis. So it's our goal, right? This is what we're after. But because it's our goal, it has to be the last thing that we find the values for. The values of wedge are going to be a function of the values of the simpler parts of the sentence. So we're going to hold on to wedge for the moment and just kind of consider it as the thing we are aiming towards, but we can't start there. We have to start with what is in parentheses first. All right. So what do we have in parentheses? We have a conditional if Q, then not P. Well, we have to think about what the negation is a negation of. This negation is a negation of P, right? So whatever the values of P are, we're just going to flip them, and we have those values. So we have to find ultimately the values for horseshoe. So what we're going to do in order to find the values for horseshoe is plug in from our reference tables the values for Q and the values for not P. So let's start first with Q, since this is our antecedent. I see over here under Q, the first value on the first row is true. So I'm going to plug that in. Q on the first row is true, because it's true right here. I then move down to the second row, and I see that Q is false. So I'm going to write false. I then move to the third row, and I see that Q is true. And then finally on the fourth row, Q is false. All right? So Q can be true, and false. Now let's consider not P. We have the values for P here on the left side of the reference column, but it's the negation of P, right? So we have to flip the values of P as they appear on our reference table. So on the first row, I see that P is true, so the first row of not P will be false. Be careful with this. We have to make sure we negate P. Otherwise, it's the exact opposite values, right? On the second row, P is also true, so not P on the second row will also be false. Now on the third row, I see that P is false, so the negation of P on this row will be true. And finally, I see that P is false, so not P will be true again. So not P is false, false, true, and true. Okay. Now let's try to think about the values for the conditional, for horseshoe. Remember what our rule is. Conditionals are only false when the antecedent is true and the consequent is false. In any other instance, horseshoe, or the conditional, is true. So let's look at our first row. I have a true antecedent Q and a false consequent, not P. So that violates our rule. So we know that on the first row, horseshoe as a whole is false. True antecedent, false consequent generates a false conditional. On the second row, I have a false antecedent and a false consequent. So horseshoe is true. Remember, you can have a false antecedent and a false consequent, and the horseshoe is still true. It's just when you have a true antecedent and a false consequent. Then on the third row, I see that Q is true, our antecedent is true, and our consequent is true, not P is true. So horseshoe is true on the third row. And finally, I have a false antecedent, Q, and a true consequent, not P. So horseshoe on the fourth row is true. So horseshoe is only false on the first row. That violates our rule where we have a true antecedent and a false consequent. I think it's useful, by the way, when you're writing these to use some different colors so we can differentiate what the values are within our more complex statements, such that we can sort of visually eyeball that these are the values for horseshoe rather than Q and not P. Okay, so now we're bringing together the values of horseshoe with the disjunction. The disjunction is not a disjunction of P and Q. It's not a disjunction of P and not P. It is a disjunction of P and horseshoe. So that's the right order of operations. We have to be moving out from Q and not P to horseshoe, and then to the disjunction of P and horseshoe to generate the values for wedge. So let's plug in the values of P, even though we kind of can eyeball them pretty easily. Let's just carry them over from our reference table so that we avoid any easy mistakes. So I see on the first row, the value for P is true. Whoops. Let me put this in red. The value for P on the first row is true. Then I look over to the reference table again, and the value for P is true. And then I check on the reference table, and the third row suggests that P is false. And then finally on the fourth row again, P is false. Okay. So now we have our disjuncts. P is our disjunct. This is our first disjunct. And really the values of horseshoe are the second disjunct. That's what we're comparing. That's the connective. Or that's what's being connected. Okay? So now we can think about the values of our main operator, wedge. Remember our rule. Disjunctions are only false when both of the disjuncts themselves are false. As soon as you have one true disjunct, the wedge as a whole is true. So let's do our comparison. I have a true value for P and a false value for horseshoe. So because we have that one true P, the first row of wedge is true. Right? Only need one true disjunct. The second row for P is similarly true, and the value for horseshoe is true. So the second row for wedge is true. On the third row, the value for P is false, and the value for horseshoe is true. So wedge again is true. Right? We have one true disjunct. And on the fourth row, the value for P is false, and the value for horseshoe is true. So the value for wedge again is true. This is another tautology, or a bit of circular reasoning. True, 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 and true are the values for our main operator, the wedge. So I'm going to box this up so we can kind of clearly see that this is the truth function, the truth values for the main operator. And this is our complete truth table. Okay, so this will take some practice to get used to, but the key for now is understanding the order of operations. So I recommend writing out a few of these for yourself. Get used to how to build the reference table in terms of following our formula. L equals 2 raised to n, or L equals 2 raised to the number of variables that the sentence demonstrates. All right? Thank you, everyone.